Alrighty, good morning everybody, and welcome back to Math 105. Plan for today, we're going to start Standard 14 and start actually getting into some proofs of the propositions in Euclid's Elements. No office hours today, but I will have my usual office hours on Monday at 10 o'clock and at 2. And as a reminder, homework 13 will be due on Monday. Or the standard 13 quiz, sorry, a little louder. Standard 13 quiz is going to be due Monday evening. Now, announcement. I was having apparently some recording issues in my class on, Friday? On Wednesday. And that for you all, the audio apparently didn't get caught at all by the camera. And one of my other classes that I was recording in this room, the video kind of cut out halfway through. So what I've done is I've reinstalled the camera software on my computer. I've also kind of gotten a new adapter to kind of hook up the camera cable to my laptop, and hopefully that issue won't happen again. But if it does, either A, you won't be able to hear this conversation because the audio cut out again, in which case this is a completely meaningless conversation to you out there, or it'll cut out somewhere partway through, and I will do my best to make it to find a fix over the weekend. So I apologize for that. Anybody have any questions or comments before we get started today? All right. So, 4 friends, been doing really well in math class, decide to take a weekend road trip instead of studying for the final exam. Poor choice indeed. Not surprising, they drink too much, oversleep on the morning of the final, get back to campus after the exam is already over. One of them concocts an explanation and asks for the professor's mercy. He says, "We went to my parents' cabin for the weekend so we could have a nice, quiet place to study. Driving back on Monday morning, we got a flat tire, we didn't have a spare, and it took hours for help to arrive." Professor said, "I understand. Here, come back tomorrow morning and I'll allow you to take a makeup." So the next morning, the professor seats the students in the 4 corners of a large lecture hall. The tests are just 1 page, already on the desk. The professor tells the students to begin. On the front side is 1 easy calculus question that all the students answered pretty quickly. On the back side of the question is an even simpler question: which tire? They all answered the same. Okay, so now we finally talked about all kind of the prerequisites to Euclid's Elements. We've gone through a lot of the necessary definitions. We've gone through the 5 postulates, and we've discussed the 5 common notions. So, the plan for what I have today is we are going to go through and prove our first proposition. And the first proposition being about equilateral triangle constructions. So on the front page of the packet, if you're following along in the packet, I included the 1 definition we're going to be relying on today, which is Euclid's definition for a circle, the 5 postulates, and the 5 common notions. So those are just kind of there so we can refer back to them when we need to. So we're going to go through proof of proposition number 1. I encourage you to bring a copy of Euclid's Elements, because if you have it, you won't have to necessarily write this down. If you want, I left you some space to write down the proof in the packet, or you could just kind of follow along in the book if you'd like. It's up to you in that regard. So here's the first proposition. The first thing that Euclid's not just going to assume is true, but actually is able to construct a logical explanation, like what we were doing back in Standard 9, to actually prove that it has to be true. And this is going to be proposition 1. On a given finite straight line, construct an equilateral triangle. Let's do a little more over here. So right off the bat, this is Euclid's first proposition. He's saying on a given finite straight line to construct an equilateral triangle. What do you think he means by this? This isn't a complete sentence. This is just a propositional phrase. On a straight line to construct an equilateral triangle. If we were to try and add a few words to the beginning of this to actually make it like a complete sentence and thus a mathematical statement, what could we put at the beginning?
Potentially, it is possible. It is possible to.
It is possible to. It's possible to, on a given finite straight line, to construct an equilateral triangle.
It is possible to construct. Wait.
Just it is possible.
It is possible on a given finite straight line. Yeah, we can quibble about the exact semantics of it, but
It is proposed.
it is proposed on a given finite straight line to construct. I think all of these are kind of valid ways of doing it, subject to grammar. I'm going to go with it is possible. But I certainly think it is proposed would also work fine here. Basically saying, this is something we saw with the first few postulates. Euclid's kind of saying it is allowed to do something, it is possible to do something with a straight edge and compass. He's just kind of leaving it out from the beginning. Just like what we saw in postulates 1 through 3. All right, so in other words, what Euclid is saying is that just using the postulates and common notions, if we have a finite straight line, like this one, from A to B, let's make it a little smaller, because I'm going to need some more board space, we should be able to construct an equilateral triangle on that. So what's an equilateral triangle? I never defined equilateral, but a term you might have seen before in previous classes.
It's the triangle where all the angles are equal and all the sides are equal.
Yes. Technically, by definition, it's just a triangle where all the side lengths are equal, which is all we're going to be proving here. This proof's not going to have anything to do with angles. But then a later proposition will actually prove that if all the side lengths are equal, then all the angles will have to be equal as well. So technically, the definition doesn't require all the angles to be equal, but we can later go on and prove that all the angles would have to be equal. So I'm okay with that. I had to think about that for a second. So here's our proof. Something to keep in mind as we're going through this archiness, the only tools we are allowed to use are the postulates and the common notions. Anything else that we might intuitively think should be true does not necessarily have to be true. So, and as we go through the proof, it's going to be telling us things like draw a circle, connects 2 points with a straight line, etc., etc. As we do that, I'm going to draw that out over to the side here, so you kind of have a visual aid for what's going on here. But here's what we're going to do. We're going to start by saying let AB be the given finite straight line. We're going to use the same sort of language we started our proofs with in Standard 9, in which when we said something like, let A and B be even numbers. Let A be an odd number. Let AB be the given finite straight line. We're just kind of saying, let this geometric object be this type of thing. And our goal then is going to be to construct an equilateral triangle. So as Euclid put it, thus, it is required to construct an equilateral triangle on A. So in other words, our goal is going to be to make an equilateral triangle where AB is one of the sides. So somehow we need to be able to come up with a triangle where AB is one side and the other two sides all have the same length as AB. So naturally, the first step in constructing a triangle is going to be to draw a circle. With center A and distance AB, let the circle BCD be described. So in other words, what Euclid is saying is, he wants to draw a circle whose center is at A and whose radius, or as Euclid put it, his distance, is equal to the line segment from A to B. In other words, Euclid wants this circle. Time out. How do we know we can construct a circle that's centered at A and whose radius is AB? How do we know that that's something that's allowed to do?
With a compass.
With a compass. Physically, yes, that's what we would do. How do we know it's we're allowed within Euclid's system to do that, though? We have a postulate that says we are allowed to construct circles whose centers are wherever we want them to be, say at A, and whose distance or radius is whatever we want it to be. In this case, let's just say the radius is the length of the segment from A to B. And so we're actually going to put in here, and put it in brackets, postulate 3, or post 3 for short. And the reason why I'm doing this is to indicate that we are using postulate 3 here. If Euclid hadn't already assumed postulate 3 from the get-go, we would be stuck. We wouldn't have been able to draw this circle necessarily, because there wouldn't have been a logical rule that necessarily says, hey, you are allowed to draw circles like this. But since we do have postulate 3, which we're just assuming is true, that's going to tell us it's totally legit to just say, yeah, make this circle. Again, with center B and distance BA, let the circle ACE be described. So now, Euclid is not only saying he wants a circle centered at A, whose radius is equal to the length of our pre-existing line segment. He's also saying we want to have a circle centered at B, whose radius is equal to the length of the line segment. If you notice something, what word is Euclid using here to say, like, we're going to draw out the circle BCD, or let the circle BCD, we'll talk about C and D here in just a second. He's not using the word let it be drawn. What word is he using?
Described.
Why do you think Euclid's using the word described here? Or rather, why is Euclid using the word that translators later translated to mean the same thing as described? Specifically saying, he's not saying let the circle BCD be drawn, just saying let it be described. I describe this circle to be beautiful. I don't think it's what he means.
Is it because the propositions are more kind of general rules for creating something instead of like just like a specific case where you just do something once and it's over with? Like if you try, if he uses describe, maybe he's trying to talk about a more general thing that's meant to be repeated.
Ooh, something that can be repeated instead of just drawn out like a single time and then potentially erased and forgotten about. Okay, so described here potentially meaning some sort of permanence to what's going on. Could be. Any other ideas or thoughts?
This is just literally shooting off the top, because I have no idea what the Greek is, and it's just as written, but is it perhaps that the word, the Greek use could be better translated as described because of the writing and the working materials that they had at that time, like, you know, would have perhaps have been, you know, paper and pen, so he's like we have, but it would have been more, you know, slates or whatever they had, you know, available. So maybe the materials they used were different, and therefore describe, like, I just see the word scribe in there, which means, you know, one who writes or one who copies or puts down. So that's perhaps more because of the type of copy work they would have done. Maybe that's why I use that word instead of write.
So use describe to talk about different ways in which the Greeks might think about drawing out these sorts of things using the materials they had at the time as opposed to what we have today. Could be something like that, yeah. There is certainly the word scribe within the word describe. Fortunately, I can't say I've read this proof in the Greek in which Euclid wrote it, so I can't tell you necessarily like, oh, this is what the original Greek word is, and here's the context in which it was used. But what I personally think is, I think when Euclid uses the word describe, he wants it to say, let this circle exist in a way that isn't necessarily tied to having this visual picture in front of us. In theory, and this is going to be something that we see later on in all of his proofs, we should be able to write all of our proofs without having a picture in front of us. None of the proofs are going to be reliant on actually having pictures to look at. It might help it can help certainly a lot to understand the proof by putting a picture in front of us and having like a visual aid of seeing, okay, yeah, I can kind of see what we're doing here. But we're never going to have to we shouldn't have to ever actually rely on the picture itself. So I think when he says, let this circle be described, I think what he means is we're going to assume we have the circle. We have the circle and that it exists, and that here as its center, here's what its radius / distance is going to be. But you can draw it out if you want to on the side, and Euclid, being a constructivist in nature, is interested in how do you construct these sorts of things. But he's interested in sort of how do you construct the idealized equilateral triangle, not necessarily a physical one that you actually construct. He's interested in using a straight edge and compass. How would you construct what Plato would call the idealized equilateral triangle, so to speak?
So he's like more interested in pure math and less of like anomalous, like that only applies to like physical things in front of us, and more saying like getting the idea of it, the perfect equilateral triangle.
I would say so. Like he wants you to know that given the things that he's assumed in his postulates, as well as common notions, you should be able to construct the idealized equilateral triangle if you had a perfect idealized compass, an idealized straight edge, and an idealized line segment AB to start with. Straight line segment AB to start with. Yeah, he's thinking of this in a very pure mathematical way, even though he's talking about constructing something, I would say. So, we got two circles. Dr. Gerstel, what's with all these points C, D, and E? We're going to get back to those in just a second. So, here's what's up next. He's going to say that, and from the point C, in which the circles cut one another, so basically you could say, hey, find a point C at which these two circles that we've drawn have to intersect each other. There's a point. There's one of those points. From the point C in which the circles cut one another to the points A and B, let the straight line CA, CB be met. points A and B, let be straight lines, CA, CB, B. So in other words, he's saying, hey, draw straight lines from this point of intersection down to A and down to B. How do we know it's allowed to draw straight lines that connect the point C to A and the point C to B?
Postulate 1.
Postulate 1. Here, we're going to throw in another postulate and say that postulate 1 says, given any 2 points, you can construct the straight line that goes between them. So there's one word that in particular that I find interesting in this last sentence. And it might not be the same word you think is interesting. I find V to be an interesting word. Because, if you remember, in Euclid's own first postulate, he just says, given any 2 points, you can draw straight lines that go between them. But when he says these straight lines, CA and CB, saying V here is sort of implying there's only one of them. So we're already getting to a point where Euclid assumed that the straight line connecting 2 points has to be unique, but he didn't explicitly say so in postulate 1. By Euclid's version of postulate 1, there could be multiple lines, but here he's kind of implicitly already assuming, by using the word V, that there's only going to be one straight line connecting your 2 points. All right, so we have a triangle here connecting points A, B, and C now with 3 straight lines. And our goal is now going to be to show that that triangle has to be an equilateral triangle. So now, since the point A is the center of circle CDB, I should probably draw the other points. Anytime that Euclid draws a circle, he's going to want to have 3 separate points that are that are on the circle. So when Euclid says, let the circle BCD be described, he wants to have a circle centered at A where there's points B on it, C on it, and some other point D. It's going to be something we see a lot of going forward, is you don't define a circle unless you can name at least 3 points on it. D and E are not going to be important to us at all in our proof. So we have them, but they're just going to be sitting there out to the side. And modern geometers are going to kind of frown at that a little bit and say, why do we have these points D and E if we don't actually use them anywhere? We're not going to use these points. They're just kind of floating out there in the ether. So now, since A is the center of circle CDB, AC is going to be equal to AB. So in other words, the length of this segment is going to be equal to the length of that segment. AC and AB have to be the same length. So why is that? This time, Euclid's not going to rely on a postulate or a common notion to say AC and AB have to be the same. He's going to rely on a definition. Or definition 15. I didn't number the definitions when we went through them in the previous package because I was going through them out of order. But definition 15 was our definition of a circle, which, if you want like a reminder, it's on the front page of the packet. Definition 15. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lines within the figure are equal to one another. Here, we're saying A is the center of the circle. It's kind of the point from which all the straight lines falling on the circle are equal to each other. here we're saying A is the center of this circle, so the straight line going from A out to point C on the circle, and the straight line going from A to the point B on the circle have to be equal to each other, according to definition 15 of the circle. So sometimes Euclid doesn't just cite common notions and postulates when he uses them. He'll also cite, I'm using this definition to say why these two lines have to be equal. It's because they're both lines going from points on the circle to this fixed point A that makes up the center of the circle. Questions or comments so far? Again, since B is the center of circle CAE, BC is equal to BA by definition 15. So in other words, since B is at the center of this circle on the right, all the lines going from B to a point on the circle should be equal to each other by Euclid's definition of a circle, definition 15. And so here, Euclid is saying these two lines should be equal, the line from B to C and the line from B to A. But CA was proved equal to AB. Thus, each of the straight lines CA and CB are equal to AB. So just kind of restating the length, it's saying that AB here, this line, the original line we started with, is going to be equal to both the line going from A to C, or C to A, excuse me, as well as the line going from C to B. It's kind of restating what the previous two sentences say. And things which equal the same thing are also equal to one another. And thus, CA has to be equal to CB. So in other words, CA, this segment right here, and CB are both equal to the same line AB. The top left and top right sides are both equal to AB. Therefore, they also have to be equal to each other in turn. CA would have to be equal to CB. And which postulate / common notion is going to tell us that our two lines, which are both equal to the same thing, AB, would also have to equal each other?
Common notion 1, those streets of the same thing are also equal to one another.
Yeah, exactly. For some reason, Euclid literally felt the need to spell that out again, or say that out again. But that's exactly common notion number 1. This will be our first use of a common notion. So CN1 just going to be short for common notion 1. And then we're basically done. We can just then say, I seem to run out of space on the board, so I'm just going to erase the first few lines here. Thus, the three straight lines CA, AB, and BC equal one another. So in our drawing, I'm just going to remove the double hash marks and just mark all sides with a single hash mark. Say now we know all of those sides are going to be equal. Thus, the triangle ABC is equilateral. And it has been constructed. On the given finite straight line AB. So in other words, we've done what we want to show. We have the three straight lines are equal to each other, and so ABC, by definition, is going to be an equilateral triangle. A triangle where all the side lengths are the same. And yes, a later proposition is going to prove that all the angles will also have to be equal to each other, but that's not necessary by the definition of equilateral triangle. That's just going to be something that falls out from using some of the postulates involving like angles and such. And if you notice, at the end, Euclid ends his proof by saying something interesting. He says, being what it was required to do. Euclid includes this at the end of all of his proofs. It's like a little bit of a flourish saying, hey, you want to do something? And I've done it. We have done the thing we said we were going to do, which is to show that you could, on a finite straight line AB, it's possible to construct an equilateral triangle using only the postulates and the common notions, as well as the definition of circles. Only using these building blocks that Euclid started with, he showed that he can do the thing that was required to do. This is kind of a choice of translation and saying being what it was required to do. There's another kind of three-letter acronym that often gets used to mean the same thing. Has anybody seen like a three-letter acronym before that kind of ends up being translated oftentimes as thus it is proved, thus it has been demonstrated? It's QED. So QED is the Latin quod erat demonstrandum. And what that just means is literally this: being what it was required to do, being what was demonstrated. And so, because these proofs are kind of long already, whenever we write out propositions on the board from here on out, I'm going to end with QED, because I like it because it's shorter. So Euclid's being what it was required to do was originally written in Greek, and then the Greek got translated into the Latin, quod erat demonstrandum, QED, and then that often gets translated back into English as thus it is proved, thus it has been demonstrated, being what it was required to do, being what was demonstrated. All different kind of ways of just translating the same original Greek phrase, which I'm not going to write on the board because I would be making a mockery of the Greek if I did. That's our first proposition. We started with just a single line segment. We used a postulate to draw two circles of the same radius, one centered at A and one centered at B. We knew we could do that because postulate 3 said precisely it's allowed to do this. We then used postulate 1 to say, hey, at the point C at which these two circles intersected, we could draw straight lines from C to A and C to B. Sorry, E, you got erased, but you never mattered anyway. And finally, we then were able to use common notion 1 in the definition of circle to say AB has to be equal to CA as well as to CB, and therefore, from common notion 1, these two side lengths also have to be the same because they're both equal to this segment from A to B. And that's how we got our equilateral triangle. Only using the postulates, the common notions, and the definition, we were able to get as our starting points, we were able to prove we can always construct an equilateral triangle. So what observations can you all make about this proof? In particular, is there any way in which Euclid wrote out or made word choices or kind of included certain phrases that you thought was interesting? Mm-hmm.
I thought it was just interesting. I've had, there's not even a, but at the very top, it says they cut one another, or things an interesting way of saying, are they neat?
Yeah, where they cut one another. It sounds like one of them's a scissors.
Yeah, exactly. And then
I think that might just be a translation thing. Like, I think cut here could mean the same thing as could just be translated from the same thing. That could also be translated to mean intersect.
it's an interesting word, though. Definitely.
It's certainly an interesting choice of translation from the whoever did this translation, if nothing else. Sorry, you have something else?
I don't think so. I think that was the thing that stood out to me. It also just seemed like, I have to remember they wouldn't really have had standardized rulers like ours today, but it seems like a lot of work to do triangles with the same size.
Yeah, it's a lot of work to construct these things. I think if you told Euclid that was a lot of work, he would say, tough. Deal with it. You're going to have to do a lot of work if you want to understand my elements. That's because Euclid definitely was a believer in hard work. I mean, he himself came up with hundreds and hundreds of these postulates, so he certainly was a hard worker.
I just thought it was interesting that when describing a circle, it had like circle, CAE or something like that. Like we usually use that for like straight lines and stuff instead of like in geometry today, instead of like all the way around having just kind of different points on a circle that go around. That just struck me as interesting.
Yeah, it's an interesting choice of notation of circle CAE. First of all, that we have this extra point E to begin with, but also, if you were to just say CAE, I might think that's, why isn't that referring to, I'm going to draw a new copy of CA and E out here so it doesn't get too muddled. If we were just to say CAE, why can't that just be the angle between CA and E? So I think Euclid has to be very careful, and anytime he mentions CAE, he has to explicitly say the circle CAE as opposed to saying CAE. I will say the reason why he has these points D and E out there is because when he refers to them later on, the circle CDB, he needs to have 3 points in order to have a unique circle. Because if he just said the circle CB, there's lots of circles that could pass that or not CBE, CBD, there's lots of circles that would just pass through 2 of these points, C and B. For you to have C here and B here, I could draw this circle that goes between them. I could draw this circle that goes between them. I could draw this circle that goes between them. There's lots of circles that pass through C and B. But only one of them that would also happen to pass through this point out here. So the reason why we have points D and E, I think, is just to make it clear that there's a unique circle that passes through all 3 of them. Whereas if we were to just say the circle going between C and B, you could draw more than one of those. Euclid never says anything about this, but it turns out there's a unique circle that will pass between 3 specified points, whereas with 2 points to start with, there's lots of ways to draw circles between them. But it is an interesting choice of notation. So one thing that Euclid did that I think really appeals to me as someone trying to read this proof, looking in from the outside, is that any time he used a postulate, a definition, or a common notion, he made sure to explicitly say so and say, hey, this is true because of postulate 1. Postulate 1 tells us we can draw these straight lines. Common notion number 1 tells us since CA and CB are both equal to AB, they must also equal each other. Something that's certainly I find very helpful is knowing when are we invoking a certain postulate, or when are we invoking a certain common notion, or when are we invoking the definition of a circle to tell us that AC is equal to AB. Because sometimes it's not clear. They'll just say, oh, this thing has to be true, and it's not clear why, unless you explicitly include, here's the thing that I'm invoking, this postulate to tell me this previous statement has to be true. That's kind of a stylistic choice I kind of like. Any other questions or comments? All right, Euclid made a big goof. Turns out there's one thing in this proof that Euclid said has to be true that he gives no reasoning for at all. And that's this piece right here. Euclid says, find the point C in which these 2 circles cut one another. Why might we be modern geometers reading this proof hate this part of the proof of the first proposition. They're fine with the rest of it, but they hate this line in particular. From the point C in which the circles cut one another. Why do you think modern geometers would not like that line?
Well, there's 2 points in which the circles cut one another.
True, there's multiple points. I think if we had picked C to be the point down here where they cut each other, we could have just constructed these line segments and just gotten that equilateral triangle. It's true that there are multiple points, and we could have. So let's say Euclid had changed this to say, pick one of the 2 points where the circles cut one another, label that as C, and then you can proceed normally from there. There's still a problem that modern geometers have with this proof, other than the fact that, like, oh, there appear to be 2 points at which they cut which the circles cut each other.
He doesn't seem to initially give a reason why C works as the 3rd point of the equilateral triangle. Like we see later on that it's because it's equidistant from both of the centers of the circles and points A and B. But initially it just seems like he's just kind of picking an arbitrary point.
And to say, like, hey, pick this arbitrary point, don't worry, I promise you it will be useful later, sort of thing. This is true. It doesn't explain until much later why he's picking this point to begin with. I wouldn't say that's necessarily a problem. Oftentimes, Euclid's going to do a lot of this. It's like he's going to define something, and it's not going to be clear why it's important until much later on in the proof.
Does it have more to do with independent of drawing to figure out we have no reason to say that point is going to exist?
Bingo. You notice Euclid's very careful throughout all these different things to cite postulates or definitions or common notions for why he's making certain claims. Why do we know CA and CB have to be equal to each other? Because of common notion 1. How do we know these 2 lines have to be the same? Definition 15. How do we know we can draw these straight lines out? Postulate 1. Euclid's very careful to give reasoning for most everything in this proof, except why do we know the 2 circles have to intersect, or if you prefer, cut each other in the first place? I'm sorry about that again. The only reasoning that we can give for that is I drew a picture, and in the picture the circles intersected each other. But Let's start writing some of this down. There's no reason, independent of the picture, why they had to intersect in the first place. I'll say there's no logical reason circles had to intersect. In the first place. This certainly appeared that way in the pictures. C appeared in the picture drawn. But here's the thing, if I were to draw a different picture for a different line segment AB, how do we know those two circles are still going to intersect when we go through the first same steps? It happened in a single picture, but our proof should be able to be independent of the picture, and in this case it's not, because we're depending on the picture for the existence of either one or 2 points where the two circles are going to intersect each other. Just kind of following up on that same point, I would say there's no reason, independent of the picture drawn, why these two circles have to intersect. Euclid goofed. He assumes something that he has no logical reason for saying. Because there's no postulate or common notion that would say those two circles had to intersect. Given those 5 postulates and 5 common notions and definition of circles, it is very possible that these two circles didn't have any points in common. The only thing that would make us think otherwise is I drew a picture and it just so happened in that picture that we had 2 different points of intersection. So let's say you were a modern geometer trying to look at this and thinking, it doesn't look like these two circles would have to intersect. What do you think modern geometers might do to help get around this issue?
Try to write out a proof that when you draw 2 circles like this on a line that they have to intersect.
Try and make it out of proof first? That's exactly what modern geometers tried for a very long time. They were not able to do so. Turns out there's no way to guarantee it. There's no way to write a proof that just relies on Euclid's postulates and common notions that would say these two circles have to intersect. I think it's a great idea. It's just one that geometers embraced for a long time. They just were not able to make it work. So what they did instead was they just made up their own postulate. Well, that's the question, how do we fix this? Modern geometers added a new postulate. And what the postulate says is that if a circle gamma has 1 point, P1 inside, and 1 point, P2 outside, another circle gamma 2, gamma prime, then the two circles must intersect in 2 points. So in other words, what they said was, all right, suppose you have a circle gamma, and there's one point on gamma that P1 is inside. So this will be our point P1 inside the circle gamma prime. And here's going to be a point outside the circle gamma prime. Well, if gamma has a point inside, 1 point inside and 1 point outside, at least 1 point inside and outside, then these two circles are going to have to intersect in 2 points. And so modern geometers are just like, all right, we need, clearly Euclid's postulates didn't work out here, didn't give us what we needed. Let's just make a new postulate. And now with our new postulate, that's going to fix the hole in the proof. Turns out, modern geometers have created a lot of new postulates. Kind of the modern version of Euclid's elements, I would say, that where everything that Euclid did wrong has been fixed, has probably something like 10 to 12 postulates built into it now. All right, that's going to do it for today. When we come back on Monday, we will look at the second and third propositions of Euclid's elements. Talk about how they build off of this first one. Hope you all have a good weekend, and I will talk to you all on Monday. Good, video didn't cut out.